Okay, thank you very much for the invitation. It's a pleasure to be here. I always like coming to IUC. In fact, we were talking with Jay yesterday and we realized I know some parts of the town better than he does. So I was trying to tell him, well, we should go left here. I'm going to be talking about some recent work of ours, flow representations of games. Here the objective is to get an arbitrary game and try to approximate it with another one which has nicer both static and dynamic equilibrium properties. And the hope is, using the proximity of the original game with the approximate, we would like to establish some properties of the equilibrium properties of the original game. This is joint work with Ozan Candoğan, Ishai Menash and Pablo Parillo, all from Leeds, MIT. So there has been much recent interest in using game theoretic models for the analysis of resource allocation in networks. And this is driven mainly by two reasons. One is that game theoretic tools or game theoretic modeling, being a model for multi-agent scenarios, how multiple agents behave in strategic environments, automatically or naturally allows a flexible control paradigm where we allow agents to autonomously control their resource usage to optimize their own selfish objectives. And the second reason is, even when we don't have selfish incentives in the picture, game theoretic models and tools have been used or provide potentially tractable decentralized algorithms for network control. Of course, when we're using game theory models, especially static game theory models, one needs to step back and do an important reality check in the sense, do game theoretic models make approximately accurate predictions about behavior or system performance? This is especially relevant in engineered systems because we would like to understand where the equilibrium state we're talking about is coming from, right? Economists have worked on this a lot, trying to justify equilibrium concepts through rationality or other informational structures. In the context of an engineered system, if we're using a game theoretic model, we would like to understand if the equilibrium is a good approximation of how agents actually behave. And to illustrate that point, let me talk about a simple and classical game, the K-beauty game. The game is as follows. We have n players. Each picks an integer between 0 and 100, let's say. And the person who is closest to k times the average of the group will win a prize. And k is a number which is strictly less than 1. Okay? So this can be 3 people, each picking a number between 0 and 100. And whoever is closest to k times the average of the 3 will win the prize. And what is the Nash equilibrium of this game? Well, one can actually do the argument, try out different candidates. If you think about each agent picking the same number, well, one can cut down slightly and then win the prize, or you can think about other candidates where they have picked different numbers. You can do the analysis and actually show that the unique Nash equilibrium of this game is 0, 0, 0. And in fact, this is the unique strict dominance solver strategy profile. Okay, this is the unique Nash equilibrium. It's a very strong equilibrium because it's strictly dominant with respect to other strategy profiles. But how do intelligent people actually play this game? And this is a game I generally make my students play in the first lecture of the game theory course. I sort of pick 3 people, make them choose numbers, and then see how they actually bid. And it seems like in the first time play, nobody is close to 0. And everybody is rational and so on. They think about it. But for instance, when k is 2/3, the winning bids are around 20 to 25. And this is also empirically tested in the behavioral game theory experiments. And the question is why? Well, if you ask the students, they say they're rational. They bid k times their expectation of the average. But in the first round, their expectation of the average is something around 40. So they expect all the people to bid around an average of 40 with a 2/3, k equals 2/3, so they bid something around 25. But this shows that they're not really, in the first play of the game, they're not accurate in their assessment of what that average is. So you make the same group play it a couple more times, 2, 3 times, at most 3 times, and then they all find the strategy profile 0, 0, 0. So essentially what happens is, as they play the game more and more, their expectations become accurate and they learn the Nash equilibrium. So this is in fact also the most common justification of the Nash equilibrium, and I think in my view the one that makes most sense for our purposes when we're using it in engineered systems. Can we model a game, make individuals repeatedly play the same game and actually expect the game to converge to a Nash equilibrium? So that's nice, but this type of convergence to a Nash equilibrium is not a general result. In fact, examples of non-convergence or convergence to non-Nash equilibrium play are easy to construct. So what do we do? Well, let's look at one specific class of games, the potential games. So I will define this more formally in a second, but potential games essentially are games that admit a potential function. In the sense, if you take a potential function, maximize with respect to subcomponents, it aligns with the maximization problem of each of the individuals. So you can view this function as a function that aggregates all the preferences of different individuals. So instead of these multiple different objectives, there is one function that can be used to capture the preferences. So these are nice games, nice in the sense a pure strategy Nash equilibrium always exists, which is not easy to establish in all kinds of games. And the second one, which is even nicer, is that if you think about natural learning dynamics, like everybody best responding to other players and so on, this converges to a pure Nash equilibrium. So this is all nice, but the problem is there are only a few games in economics, social sciences, or even networks that are potential games. So this motivates the question, even if a game is not a potential game, can we actually say it is close to a potential game in some sense? And if so, it may actually inherit some of these nice properties, existence of an approximate pure Nash equilibrium, or convergence to an approximate Nash equilibrium in the dynamic sense. And the questions then associated with this is, how do we determine whether a game is close to a potential game? What is it that these potential games have? What is it in the preference structure of the users that allows one to actually end up with a potential game? And if you think about arbitrary games, can we think about natural decompositions into these simpler potential or other structures? And another one is, can certain games be perturbed slightly to turn them into potential games? So maybe we can use some of these ideas in the game design, maybe changing the utility function slightly so that the resulting game turns out to be a potential game. So the main contributions of the work then is as follows. We're going to analyze the global structure of preferences. And actually, one representation that will allow us to do this will be representing finite games as flows on graphs. And this will allow us to do a canonical decomposition of arbitrary games into three components: a potential game, a game which we refer to as an harmonic game, and a non-strategic component. Now, given this decomposition, we're going to establish projection schemes using convex optimization. Given a game, we can actually figure out what each of these different components are. We're going to present closed-form solutions to the projection problem. And then what I was sort of arguing before, we're going to try to characterize approximate equilibria of a game using equilibria of its potential component. And similarly, we're going to try to analyze dynamics in a game using the convergence properties of the dynamics in its potential component. And I'll try to illustrate some of these ideas in the context of a wireless control problem at the end, power control problem. Okay, so let me now start by more formally defining some of these concepts. Let's start with the potential games. So throughout, my focus will be on finite games in strategic form. We have a set of players denoted by this calligraphic M. The strategy spaces of the players are denoted by this EM. And the utilities, we're going to represent the preferences in terms of utilities, utility functions. Utility function of a player is a function UM, which is from the joint strategy profile space into real numbers. So we say that G is an exact potential game if there exists a function phi, again mapping from the joint strategy space into R, such that if you look at, for instance, let's look at the right-hand side, fix the strategies of all the other players to x minus m. Okay? And look at a pairwise deviation from xm to ym and the corresponding utility difference for player m. This is equal to the difference in the potential function for that same pairwise deviation. And this is true for all m, in the sense you take the utility function of any player, and the pairwise deviations are captured by this by this potential function. And that's what I meant by there exists this function that can capture or aggregate the preferences. So this is the notion of an exact potential game when these differences exactly align. A slightly weaker notion is an ordinal potential game, which does not use cardinal information. It just says that the utility differences agree in sign, in the sense this is positive if and only if this is positive, strictly positive. Okay? So it's slightly weaker, but still captures the same idea, will yield the same properties, as we will see in a second. So potential aggregates the incentives of all players. One nice example of a potential game is this congestion games that are used extensively in describing behavior in wireline or wireless sometimes networks. Essentially, these are games where we have congestion externalities. Payoffs depend on the congestion created by the aggregate action of all the other players. So please stop me at any point. Any questions on the potential games definitions? It's clear, right? Yes?
One can think of that as a Lyapunov function.
Exactly. Exactly. So essentially, these are games which admits the Lyapunov function for their analysis. So let me quickly define the concept of a Nash equilibrium. A strategy profile X is a Nash equilibrium if no player can unilaterally deviate and actually profit from that unilateral deviation. In the sense, if you fix the strategies of all other players, XM yields XM is the best response for player M. Okay? So now let's try to sort of go over the properties of potential game one more time with this definition. So let's think about a potential game with a potential function and think about its global maximum. So the global maximum of a potential game will yield the best response along each of the subcomponents, right? So essentially that will automatically be a Nash equilibrium of the pure strategy Nash equilibrium of the game. And not only the global maximum, also some of the local maxima even. If you think about if the local maximum is such that it is maximizing the potential function along each of the subcomponents, that's also a Nash equilibrium. So this is nice because in finite games, we know with a potential function, a global maximum exists, right? It's just the maximum value of the potential function. So that's automatically a pure Nash equilibrium. So we automatically have the existence of a pure Nash equilibrium. Yes?
What do you mean by pure strategy?
Pure strategy in the sense, I'm not thinking about randomizations over the strategy profiles. It's just that. So if you're thinking about a finite game, EM is a finite set. So we're thinking about strategies, pure strategies in that finite set and deviations with respect to those pure strategies. So you can also think about a continuous game and think about continuous potential games, but then one needs to have certain qualifiers, right? We need compactness, we need continuity so that we can establish existence of a maximum for the potential function, which will again be pure Nash equilibrium of the continuous game. So some of these notions extend, most of the notions extend to continuous games. My focus will be on finite games here. So every finite potential game has a pure equilibrium. Moreover, many learning dynamics, such as better reply dynamics, fictitious play, or spatial adaptive play, I'm not going to define them in detail, but these are form of best response type dynamics. Either players are best responding to actions of other players or empirical frequencies of other players, or they're using some form of smoothened best response, like a logit type best response in the case of spatial adaptive play. And it is known that any of these natural learning dynamics converge to a pure Nash equilibrium in finite games, in finite potential games. So these now essentially motivate the question originally I posed: when is a given game a potential game? What are the obstructions or underlying structure in the preferences, which I will try to elaborate. So let me talk a little bit to get a sense of what is the structure in the preferences that allows us to say a game is potential. Let me try to elaborate some of the conditions that people have studied, some characterizations of exact or ordinal potential games. For that, I need this notion of a path. This is very much like if you're thinking about the graph notion, graph theory notion, it's very similar. A path is a collection of strategy profiles, and this is in the set E. So it's a vector of strategies of all players. X0 is one, Xn is also a strategy profile, such that Xi and Xi plus 1 differ in the strategy of exactly one player. Okay, so we're thinking about going from one strategy profile to another by changing only one of the strategies of the players. And for any such path, we can define sort of improvement along the path by I of gamma. It's essentially we look at the at each point, at each step I, we look at the agent whose strategy is modified, and we look at the payoff increase or payoff change in that strategy, in that player's utility, and we add them up over all n. So I of gamma is essentially aggregating these payoff differences along this path, and we say that the path is closed if x0 is equal to xn, so it's a cycle. Okay. So one nice characterization of Monder and Shapley, who originally actually studied the properties of potential games, is that a game is an exact potential game if and only if, for all cycles gamma, I of gamma is equal to 0. And this is, I'm not going to go into the proof, but the idea is not too hard to, at least, well, in both directions, not too hard to understand, right? You're thinking about a cycle. You start with a strategy profile. You end up in the same strategy profile. If I of gamma is not equal to 0, let's say if it's positive, that means you have increased the strategy, the utility differences along that cycle. But the utility differences are the same as the potential function differences. So you have increased the potential function value along that cycle. But you ended up in the same strategy profile, so you get a contradiction. So, and the other thing is it's sufficient to check, you don't need to check all cycles, but just those which have length 4. Yes? Yes.
And then how is this result related to that gradient vector?
It is related, so it is. This is for finite games again. For continuous games, there are also similar results. That says basically the gradient vector along that has to actually if you look at the along that cycle, that has to integrate to 0 basically.
That almost means that function is integrable.
Yes. Yes. But this is, I mean, it's slightly different, again, definition, but the idea is similar. I'm not sure about this part of the argument for continuous games. This part of the argument for finite games follows from just looking at the space of cycles for finite games and showing that cycles of length 4 actually forms the basis for that space. So you're actually fine only checking cycles of length 4. So that is what this first bullet is saying. If this I of gamma was not equal to 0, then it would increase the value of the potential when the cycle is completed. But the nice thing about this characterization, which allows us also to visualize these potential games in some space of games, is that the realization that the condition for existence of exact potential is linear. So that's nothing but checking, looking at these differences in utilities. So it's linear in the utilities. And then checking whether that's equal to 0. So it's a linear condition, which tells us that the set of exact potential games, when viewed as a subset of the space of games, let's say in the utility space, it's a subspace. And the other important point to realize is that the set of exact potential games is small. So it's really thin subspace in the whole space of games, and one can actually establish that formally through this dimension argument. Think about a finite game with a set of players M, joint strategy space E. The dimension of the space of games is here, so we can actually think about that's pretty straightforward to establish. Think about a 2x2 game. We have two payoff matrices, right? So the number of independent or degrees of freedom we have is number of product of the number of strategy profiles, which is here, times the number of players in the game. So that's essentially the dimension of the space of games. And for the dimension of the subspace of exact potential games, one needs to do a more elaborate argument counting the number of independent cycles. Because you're essentially going to write conditions along those cycles, right? You count the number of independent cycles, and then you subtract it from this number, because each of these conditions essentially takes out 1 degree of freedom. So if you do that exercise, this is the dimension of the space of exact potential games, and when you compare these two numbers, this is much smaller than this. Okay? So we're thinking about the space of games and the subspace that lies in there, which is the exact potential games. Let me also briefly mention, by the way, for ordinal potential games, all the nice features that I talked about also holds, because I didn't say any cardinal information when I'm making the, when I was explaining, for instance, existence of a pure Nash equilibrium. The same argument holds for ordinal potential games as well, and also similarly, convergence of dynamics also holds for ordinal potential games. Warneveld and Nord gave also an equivalent characterization for ordinal potential games in terms of these weak improvement cycles, which are essentially, you look at cycles and you make sure that the utility of the player whose strategy is modified is non-decreasing along this cycle. And at least in one step, it's strictly positive. A game is an ordinal potential game if and only if it contains no weak improvement cycles. So this is a similar type of characterization to exact potential games. Okay, so given that we understand how to characterize these potential games, let me give a simple example. Let's think about a 3-player game. And let me assume that the strategic interactions are described in terms of this directed graph. And what this says is basically utility of player 3 depends on his action as well as the action or the strategy of player 1. Okay, so more concrete example, let's assume that everybody picks a number in the set 0, 1. And the payoff of player I will be -1 if its strategy is the same as its successor, and 0 otherwise. Okay? So let me actually try to represent these preferences on the space of strategy profiles. So strategy profile is a triplet in this case, right? Each of the players picks 0 or 1. So here are the different strategy profiles. And here, so what we draw here is basically just a path, namely one of the strategies of the players is changed going from this profile to the other one. And the direction of the arrows represents the utility increase in the deviating player. Let me just make sure the things are correct. Let's pick 1, 0, 0. So from here to here, the second player's strategy is modified, right? From 0 to 1. So let's look at the utility of the second player. Here, second player and third player, their strategies match. So his second player's payoff is -1. And here, their strategies differ, so his payoff is 0. So it's basically a utility increase for player 2. So if you do the same exercise for each of these along these paths, what we can see is this red cycle here, right? Along which actually we have strict increases in the utility of the players, which shows from the previous characterizations that this game is neither an exact nor an ordinal potential game. So, okay, so that brings the question, what's the global structure of these cycles? So when we have cycles, it seems like it takes away from the property of being potential, right? So we would like to understand basically the topological structure of these preferences to be able to say when we have a potential game and when we have, let's say, something else, what's the remainder of that game. Since we're thinking about flows on graphs, it looks like vector fields. So it's very conceptually similar to the structure of continuous vector fields. There's a well-developed theory from algebraic topology to study the structure of these vector fields. We need the combinatorial analog for flows on graphs. Okay? So that's my next step. So how do we analyze the structure of flows on graphs? And essentially, the ultimate goal will be to be able to decompose these flows on graphs. So let's think about first general flow on a graph and think about how we can decompose it. I need a little bit of notation before I can do that. So let me think about an undirected graph G with a set of nodes denoted by E and a set of edges denoted by A. So we define the set of edge flows on this graph as a function x from the space E times E into R, such that if you think about the flow on any edge, xpq is equal to minus xqp. So think about this x as flow on the edges of this graph. Let C0 denote the set of real valued functions on these nodes E, and C1 denote the set of edge flows. I will define two operators that will be relevant to this decomposition. The first one is a combinatorial gradient operator, which takes a function defined on the set of nodes and takes it to a function, to an edge flow. Essentially, what this delta 0 does is takes a function phi, and for any pair PQ, essentially generates the difference, right? This is like a gradient, but it's a discrete version of a gradient. It just looks at the difference along the edges. And this W is nothing but an indicator function for the edges of the graph. Namely, you define this difference. This difference is defined over the edges of the graph, and it's equal to 0 if that's not an edge of the graph. Okay? So that's the gradient operator. The second one is I want to somehow characterize the circulations or the cycles in these flows. And for that, I define the curl operator as I look at the triclics of the graph. Think about triplets in the graph, PQR. So these are the triclics, PQR, such that PQ, QR, and PR are in the edge set. And the curl operator takes an edge flow and then calculates the sum of the edge flows along these triclics. Okay, so it essentially characterizes the cycle along the local cycle along these triclics. Okay, so those are the two operators. And using these, I'll try to just to what? Sure. Okay, so I won't use it too much actually. I'll just I put this because it's useful in the next theorem, but I won't define the next theorem in terms of operators. I just need it for some definitions. I can come back and then we can. So essentially, I'm here only defining this gradient operator and the curl operator. And the gradient is the one which sort of talks about these differences along the edges, across the edges, and the curl operator looks at triclics and sums up the edge flows across this.
What was phi again?
Phi is just some arbitrary function on the set of edges. So here is the flow decomposition theorem that our theory will develop on. Essentially, it's the Helmholtz decomposition. Hodge is used for higher dimensions. That's not necessary for our purposes. This allows an orthogonal decomposition of the space of edge flows into three vector fields. The first one is the gradient flow. And essentially, this is the globally consistent component. And essentially, globally consistent is just an edge flow. An edge flow is globally consistent if it's the gradient of some function f. Okay? So this is the first vector field, the gradient flow. The second one is the harmonic flow, which is the locally consistent one but globally inconsistent. And what is locally consistent? An edge flow is locally consistent if it's in the kernel of this curl operator. So you look at these triplets, and essentially you don't have these local cycles in that edge flow. And that's the locally consistent component. And the third one is whatever remains, the curl component or the locally inconsistent component. Okay? So let me, instead of writing it in terms of those operators, the cartoon actually is the cartoon representation of the theorem. Given any arbitrary edge flow, we can represent it in terms of the gradient flow, which is the globally consistent part. This comes from the gradient of a function. The second part is the harmonic flow, so it doesn't go around locally, but it may actually go, it may create global cycles, so it doesn't have local cycles in it. And the third one is the locally inconsistent one, which actually creates these local cycles. Okay? So given any edge flow on a graph, we can represent it in terms of these three components. And these three spaces essentially are orthogonal to each other. Okay? So this is for general flows on graphs. The roadmap from now on is to represent an arbitrary game as a flow on a graph, and then do this decomposition, and then show that this is nothing but the potential component. This gives rise to another nice class of games called the harmonic games, and this part actually doesn't exist in a game. Okay? Okay, so that's our agenda. So let me start by just arguing how we can do a flow representation in a game. So that will be very similar to the example that I talked about, right? I will define the graph in terms of strategy profiles. So, and then I will think about edges between these strategy profiles only if the two strategy profiles differ in the strategy of one of the players. So for that, let me just define a few things. We call a pair of strategy profiles M comparable if they differ only in the strategy of player M. So the set of comparable strategy profiles are those which are all M comparable, set of all such pairs. And the notation will be, so the E is the set of strategy profiles. Set of pairs of M comparable strategy profiles will be AM, and the set of all comparable strategy profiles will be A. Okay? So again, nothing fancy. This is just saying that you have two strategy profiles whose mth component differ. And this is all such pairs of strategy profiles. And the game graph is defined as this undirected graph, with E being the strategy profiles, and the links being these A, which are all strategy profiles which are comparable. So how do we define the flow generated by a game? Well, we have this indicator function Wm, which says that P and Q are M comparable. And we define a difference operator. This is similar to the gradient operator as before, but for that particular player M. Namely, we look at P and Q, which are M comparable, and we define the difference between these two. And then once we do that, we can define the flow generated by a game X as the sum of over all players dm/um. So again, the picture is similar to the example I gave before. Think about all strategy profiles, right? And dm/um gives the utility differences in the deviating players, right? And then you essentially add all such utility differences to generate that flow on the graph. Okay? Okay. So before I apply the Helmholtz decomposition to this particular flow, let me just briefly mention one difference or one important property of games and equilibrium concept that is relevant to this decomposition. And that's the notion of strategically equivalent games. And it's a very interesting notion that actually may have a lot of potential for future development. So this is basically this following simple idea. Think about following two games. One is the famous Battle of the Sexes. It's basically a coordination game. You have male and a female, and the strategy is spaces are going to a football game versus ballet. They want to go together, but of course they have each different preferences, and these payoffs basically encode those preferences. I generally explain this game in terms of lit student and an ORC student, and each wanting to go to their different colloquia, but essentially it's the same idea. So it's a coordination game. So here is the payoffs that are generally used for analyzing Battle of the Sexes. Let me think about a slightly modified version of this game. So what this game is, look at the column player strategy O. What we did here is add a constant 1 to the payoff of the row player. So instead of 3, it became 4. Instead of 0, it became 1. Okay? So this kind of change in the payoff structure doesn't change the pairwise comparisons or the utility differences at all. So if we're thinking about the flow generated in the way we defined before, because we were only defining the flow in terms of utility differences, this one and this one gives rise to the same flow structure. So they're indistinguishable if you think about the flow generated. Moreover, these two games have exactly the same same set of equilibria. Why? Because equilibrium is defined, again, with respect to these pairwise comparisons. So that's why I call these two strategically equivalent. The payoff structures are different, but the equilibrium properties are the same. Flows generated are also the same. So to be able to fix then a representative for strategically equivalent games in the space of flows, we define the notion of games without any non-strategic information. And that's nothing but we say that a game is, with utility functions UM, does not contain any non-strategic information if essentially what we do is we add up these payoffs here, fix P minus M, add up the utilities over all PM, and make sure it's equal to 0. So what this is saying is just fix that constant here. Okay? And we fixed it arbitrarily to 0 because it's easier to work with. So you have a bunch of a class of strategically equivalent games. We fix a representative for that class by making sure that this constant that is being added satisfies this property. Okay? So here is then the decomposition for the game flows. When going from utilities to flows, the non-strategic component is removed. As I tried to argue, the non-strategic component gives rise to the same flow, so first I remove that. And moreover, since we start from utilities, not preferences, these flows are always locally consistent. So if you think about these triplets or the tricliques, and if you think about utility differences, the utility differences along these tricliques is always equal to 0. So there is nothing that actually is locally inconsistent in this space of flows. Therefore, we only have two flow components, the potential and the harmonic. Okay, so thus the space of games has a canonical direct sum decomposition, which is the potential part, the harmonic part, and the non-strategic part. Okay, and these components are orthogonal spaces. So this is essentially, let me try to step back for a second. And what this is saying is if I have an arbitrary game, what I can do is I can actually remove the non-strategic part, and then I can decompose that into two games, potential game and a harmonic game. Okay? And it's the sum of the direct sum of these two games in the sense of it's the direct sum of the payoffs. Yes?
What's the scalar product?
I have not defined the norm here, but there exists a norm which actually appropriately scales with the number of strategies of each user, and just gets the, it's a weighted L2 product between the games. Yes?
Maybe I'm missing something obvious, but the first step of removing the non-strategic component, is that necessary?
So the problem is, so when you don't have that part, you mean why do I have the third component here?
No, the first, yeah, I mean, why do we need to remove, on the previous slide you argued that you add up the utilities to 0 for it.
So, but what I want to do is I want to have an arbitrary game And then from that arbitrary game, generate these different components, right? So 2 arbitrary games will be equivalent up to that constant value. So I remove that, and then remove whatever is left, and decompose whatever is left into 2 components. That's what I mean. So,
Maybe we can take it offline.
okay. That's it. Maybe my explanation. That's the way I understand. I mean, if you go through the proof in actually mapping each of these components, that automatically pops out. But I view this way of sort of seeing the decomposition as clear. Okay, so let me just give a simple example. For instance, bi-matrix games, 2-player. 2-player, and I think same number of strategies for this example. So think about the game given by the 2 pair of matrices A and B, and assume for simplicity that the non-strategic component is 0. Okay. Then we can figure out the potential and the harmonic components in, they're given by simple explicit formulas. So let me actually look at this gamma first. Gamma is okay, we have to think about it in detail, but very high level. It's the difference between the payoffs of A and B. And one can view that as a difference in the payoff structures, or a disagreement in the payoff structures of the 2 players. So if you actually assume that gamma is small, okay, so A and B are close to each other, S is nothing but what also people refer to as the team component. And this is the A minus B over 2, which is sort of like the zero-sum part. So potential component, if gamma is small, the potential component is essentially the team component, and the harmonic part is the zero-sum component of the game. Okay? This slide was for Professor Bashar because he has this decomposition in one of his papers. So it's basically, bi-matrix game can always be decomposed into a team component and a zero-sum component. But what this is saying is it's actually slightly, if you're thinking about the closest potential game, it's slightly off, and that off term is really given by this difference matrix. Okay? Okay, so let me then talk a little bit about the projection part. I talked about this decomposition. Now, hopefully motivated you, given an arbitrary game, to find the closest potential game. How do we find that closest potential game? Well, we solve the following 2 problems, convex optimization problems. The first one takes the flows. These are the pairwise differences, right, generated by the game, the original game, and then tries to find some phi, some function, such that if you look at the gradient of that function, these 2, the difference between the 2 is minimized. Okay, so this will be a potential function that best represents a given collection of utilities. And given this potential function, you can also construct the utilities that represent this near potential game by solving an additional optimization problem. In the sense, you fix this phi that you obtain from here, and you make sure that given the the utility differences here are given by the utility differences generated by the potential function. Okay? Is this clear? So first we find the potential function by minimizing the difference between the pairwise comparisons, and then we generate utility functions that exactly yield those pairwise comparisons. And these are least square problems, so the solution is straightforward to write down. If you assume that all players have the same number of strategies, the optimal projection actually is given in closed form by this phi. This is the potential function, and here pi m is a, let me go over it slowly. So pi m is an operator, it's a projection operator to the orthogonal complement of the kernel of dm. So, and the um hat is given by essentially I minus pi m um plus pi m times phi. This is our potential function here. This dagger notation is just a pseudo-inverse. So let me not, it's just, try to give an idea why that's the case. For form of the potential function follows from the closed form solution of a least squares problem, the normal equation. Essentially, this is what phi solves. This is the normal equation. Okay? And for any m, basically what we do is here, this is pi m phi, and this is I minus pi m um. So you can think about, if we're given a utility function um, this and this parts are the strategic and the non-strategic components of the utility of player m. Why? Because this pi m um, it's a little bit maybe not clear to describe online, but just to give you a gist of the idea, what we're doing here with pi m um is we're projecting to the orthogonal complement of the kernel of the m. And that pi m um actually has the same pairwise comparisons as um, but also at the same time satisfies this property of no non-strategic information. So pi m um, this projection, okay, let me say it this way. This projection is a fancy way of writing, remove the constant out, okay, and have the same pairwise comparisons. That's why I call this the strategic component. And the rest of the um minus pi m um is the non-strategic component, which is the constant that doesn't change the equilibrium properties. So because now phi solves pi m um equals pi m phi, the optimal um hat, or the closest um hat, is nothing but the non-strategic part plus the strategic part of the potential function. Okay? So that's the closed form solution. Um hat is nothing but the non-strategic part of um plus the strategic part of the potential phi, which is supposed to capture the closest strategic part of the utilities um. Okay? That's okay. So this is a nice closed form that one can actually use to compute these closest potential functions. So wrapping up, what we have here is a nice canonical decomposition. I haven't talked much about the harmonic games, but in the paper, actually, we show that similar to potential games, harmonic games also has nice properties. In the sense, we can characterize the equilibria. Actually, generically, it has a unique mixed strategy Nash equilibrium, which is uniformly randomizing overall strategy profiles. It also has some nice dynamic properties. In this, we haven't been able to prove the global stability yet, but it at least seems to, it has nice local stability properties. So the dynamic properties also seem to be nice, similar to the potential games. So essentially what this decomposition allows is provides classes of games with simpler structure for which stronger results can be provided in terms of what the equilibria are, existence of equilibria, and dynamics of equilibria. And moreover, this yields a natural mechanism for approximation for both static and dynamic properties. This is in the sense of, if I have an arbitrary game, I can look at its projection to the potential, exact potential space, and use the Lyapunov function of this to analyze, for instance, dynamics in the other one. So that's what I mean by approximation in the dynamic sense. In the static sense, of course, the equilibria of a game and its projection are related. One can show the following result. Any equilibrium of G hat is an epsilon equilibrium of G, where epsilon actually satisfies this relation. It's less than or equal to the distance between these two games. Okay? So provided that the projection distance is small, equilibria are close to the equilibria of the initial game. So this can be, for instance, used in computation of equilibria. If you're actually interested in computing the equilibria of, or approximate equilibria of the original game, you can think about computing the equilibrium of the potential component, and that will give you an epsilon equilibrium of the original game. The projection framework can also be used to study convergence of dynamics. I'm not going to give the general result here, it's in the paper, but I will illustrate this point using this power control application. But in general, essentially, the result says when you apply any of these dynamics that I talked about to the original game, I can use the Lyapunov function of its potential component to actually analyze. Essentially, you're going to view the utility differences as a perturbation from the Lyapunov function, and you can actually write or characterize the set to which the dynamic trajectories of the game converges to in terms of, again, the distance between the two games, and in terms of other parameters related to the utility functions in the two games. Okay, I will illustrate it using a simpler example. Okay, so just one more example before I go into the power control game. This is an average opinion game on a graph. Again, here it's a graphical game in the sense, this player's payoff depends on the strategies of the neighbors. So the game, the average opinion game is as follows. Each of these players pick a number from a finite set, let's say 1, 2, 3. And the payoff of each of the players decrease by the deviation of his own number from the median of his immediate neighbors. Okay, that's the average opinion game. One can show that this game is neither an exact nor an ordinal potential game. But with a small perturbation in the payoffs, it can be projected to the set of potential games. And here are the payoffs. I don't know if you... This is the strategy spaces. You have something like 243, I think. I don't remember the exact number. Those are the number of strategy profiles and the corresponding utilities in the original and the projected game. So original payoffs are the straight lines, and the projected payoffs are these dashed lines. I don't know if you can see the difference, but this shows that there's actually, you can get a game which is not exact or ordinal potential, perturb it very slightly, and get one which is a potential game. Okay, so in the rest of the talk, I'm just going to... It changes in the, well, I don't know the exact perturbation right now. It's not exactly the same as the equilibrium of the original game, but I believe it's the error is smaller than the bound that I have shown before. I don't remember.
The reason I'm asking is in studying nonlinear systems, you can have a Lyapunov function for a nonlinear system, and then you perturb the system a little bit, and improve the stability actually of the perturbed system using the original Lyapunov function itself. It's not even an epsilon change in the equilibrium. I was curious, since your result basically said that you have an epsilon equilibrium in the perturbed game, it's possible that the potential function could be used to prove
stability.
Stability of the actual equilibrium.
That's a
necessarily have, I mean, that's a bound certainly.
Mm-hmm.
Saying there could be situations where actually
There may be. We haven't looked at that. That's another.
there might not be an equilibrium, but if it does, if that does exist an equilibrium,
Yeah.
it's possible that the same potential function works even for the system.
Yeah, we haven't checked that here, but it's very useful. It would be a good idea to check that, yeah. Okay, so let me try to illustrate it by a simple power control game, these ideas. So this is one of the well-studied power control games, maybe simpler version of the power control game studied in the literature. So we think about a set of mobiles 1 to m sharing the same wireless spectrum. We have single channel, so we're not thinking about multiple channels. We denote by P the power allocation vector of the mobiles, and we assume that there are some power, the strategy sets of each of the, or the power constraints are given by PM lying in the set with a lower bound and an upper bound. Upper bound, of course, is a constraint on the maximum power usage. Lower bound is a minimum QoS constraint for the mobile. So the rate is given by the usual log 1 plus gamma SINR expression. Gamma is the spreading gain, SINR is the signal to interference noise ratio. We have the noise part here as well as the channel gain. HMMPM is the received power for player M, and the rest is just the interference from the other individuals. So each user is interested in maximizing a net utility, which is basically rate minus some power cost. Lambda m here is a user-specific price per unit power. So we refer to this game among the users as a power game. Of course, there are some strategic coupling, so we have a game at the end. It's not a potential game. Existence of a pure Nash equilibrium is immediate because the underlying game is a concave game. So we don't have any problem with existence. We are also interested in this case in approximate equilibria, and we formalize that using this epsilon Nash equilibria. Epsilon Nash equilibria is nothing but Nash equilibria where you allow for pairwise improvements up to epsilon. So let's now think about sort of a slight twist in the objective. We have a central planner, and he wishes to impose a general objective on the system. Let's say U0 is the system utility function, and we have P star being the optimal solution of this problem, and that's the desired operating point. So this has nothing to do with the game. P star is an arbitrary operating point that the system planner wants to pull the system to. And the only degree of freedom he has is on these prices, lambda m. So the question is, can he actually pick the prices lambda m such that the equilibrium of the original game actually approximates this P star, which is the desired operating point? Okay? So it's a slightly different problem. Not only are we interested in dynamics, but also there are these prices which we would like to design so that the equilibrium actually gets close to this system operating point. So we do that using the following idea. We approximate the power game with a potential game. So we consider a slightly modified game where the utility functions are given by log gamma SINR. So we just get rid of that 1 plus. This is the usual trick, I think, in turning this problem when viewed as an optimization problem into a convex problem. But I'm not doing that. I'm not doing any approximations here. I'm just considering a related game where the utilities are given by log gamma SINR minus the prices. And I refer to this game as a potentialized game for the reasons that I'm going to show in a second, because this is a potential game. And moreover, for high SINR regimes, when gamma is large, or when SINR is large, these Rm tilde is similar or close to Rm. Therefore, this is a good approximation of the original game. So the modified game is a potential game. The corresponding potential function is given by this function here. G hat has a unique equilibrium because this has a strictly concave utility function, potential function. And also, potential function suggests a very simple linear pricing scheme. If we think about P star as the desired point, if the prices are given by 1 over PM star, just take the derivative here, or the gradient with respect to PM star, then the unique equilibrium of the potentialized game coincides with P star. So what we're going to do is we're going to impose these prices on the original game, okay, because this game is close to the potential game. These prices achieve the system operating point for the potentialized game. I will apply these prices to the original game, and the hope is that the equilibrium of the original game along the dynamics will approximate the system operating point. So we will study the dynamic properties of the original game when the prices are set equal to lambda star. And I will consider a simple class of dynamics, the best response dynamics. Users updates a strategy to maximize its utility given the strategies of other players. Here is the best response mapping. Fix the strategies of the other players and just maximize the utility. Discrete time best response dynamics is nothing but update your power to be not necessarily equal, just smoothen it a little bit. Don't set it to the best response, but just take a convex combination of the current profile with the best response. Instead of looking into discrete time version, we look at the simpler or easier to analyze continuous time version, which is that just PM dot is the best response minus PM. Continuous time best response dynamics also has been studied in the literature, and people have established properties or similar properties to fictitious play as well as the gradient play dynamics. So if users use best response dynamics, continuous time best response dynamics in potentialized game, their strategies converge to P star. This was shown through a Lyapunov analysis using the potential function in Hofbauer and Sandholm's paper. Our interest in studying convergence properties of best response dynamics when used in the power game. Okay? And the idea is what I tried to elaborate on before. We use perturbation analysis. We're going to view the difference between the utilities of the original and potentialized game as a perturbation, and use the Lyapunov function of the potentialized game to characterize the set to which the best response dynamics applied to the original game converges. I'm actually out of time, right? Okay, good. So let me quickly show our results. Basically, we can show that we can provide error bounds. From now on, I think it's pretty straightforward. Given the parameters of the system, we can provide error bounds on the set to which the best response dynamics applied to the original game converges. And our notion of convergence here is uniform convergence. We say that the dynamics converges uniformly to a set S if it actually gets inside that S in finite time for any initial operating point. So we can show that actually the best response dynamics applied to the original game converges uniformly to an epsilon equilibrium set of the potentialized game, where epsilon satisfies this relation. Okay, gamma is the SINR, spreading game, and this is the lower bound on the SINR. Note that I don't even care about best response dynamics converging to the Nash equilibrium of the original game. All I'm trying to do here is to establish how close it gets to P star at the end. So I first characterize this I epsilon, or the epsilon approximate equilibrium of the potentialized game. And then one can actually say how far the power allocations in I epsilon are from P star. Okay? So that's just using strict concavity and this additively separable structure of the potential function. And moreover, one can use some other smoothness assumptions on this system utility to say that so P tilde is in the set that we converge to uniformly. And this differs from the original desired operating point by this error bound, where epsilon was what I talked about before, and some other constants or parameters related to the system. Okay? So essentially the idea is this gives us a way of getting an arbitrary game whose dynamic properties we don't know how to establish, look at a close potential game, and then use those properties to establish the approximate neighborhood that this dynamics converges to. And there's a numerical example which shows that actually the results are much better than what the bounds predict. Our bounds seem to be not very tight, but that's also related to the fact, related to the potential function that we have picked. This is not the closest potential game to the original game. We have some current work which is actually improving this quite a bit, choosing different potential functions, different potential games, and actually tightening the error bounds. So here's the summary. So we try to analyze the global structure of the preferences. We sort of decompose an arbitrary game into potential harmonic components, and then use this approximations to study either the equilibrium or the dynamics of the game. So this essentially enables extensions of the tools we know for potential games to arbitrary games.
Thank you very much.
Sure.
We only have time for a couple of quick questions.
I wonder if that can also be used when you change, when you're trying to go into things like robust implementation, where what you're changing is not. So what you're changing here are the utility functions, right? What you're considering.
I'm not changing.
Perturbation in utility.
I haven't talked about that. I mean, I have not changed the utility functions. All I did was analyze the original game using its approximation.
Right, but then I can look at it the other way and say, I start from the potential game, and your result is basically a robustness result of a perturbation of that potential game, right?
Yes.
So then I'm wondering if you could do the same thing when you're looking at robust implementation, where what you change is actually the notion of rationality, right? Then you
that's a little tricky. I mean, I think we can do it in the context of engineered systems, where we're thinking about how do we change utility functions by providing some form of incentives and so on. But when you talk to an economist, they're more strict about these rationality concepts. You have to be more careful about what do you mean by changing utility functions, or I think so. It's a good idea to use this in the context of game design or implementations, but it requires some careful modeling and analysis in terms of what kind of incentives can be provided and so on.
Well, early on, I think your first slide said that there are not that many potential games. And we have some intuition on how many real applications can be mapped into games that are approximately potential games. An example, obviously, here.
This is just one example. I try to sort of justify my statement by showing this dimension results, and the exact potential games is really small. So the hope is, I don't have a sense of all practical applications and how far they would be from potentials, but the hope is, some of them can be close to potentials, some of them can be close to harmonic games, and we can actually use these proximities to be able to say something. If they're not close to either, there's nothing we can do. For instance, one nice example is this Shapley game, which is known to have awful dynamic properties, doesn't converge to Nash equilibria at all. And that seems to be a game which is not close to either. So, but at least it gives us sort of a nice perturbation or robustness result. You start from like a Shapley game, their projections, and you start perturbing it. And up to what point can you actually allow these error bounds make sense? Yes.
There's a connection to substitute valuations.
Substitute meaning?
You have a substitute property, a substitute value.
Strategic substitutes?
Well, a valuation function has a substitute property, like one price goes up.
Yeah, strategic substitutes, yeah.
You can do projections and some of that's...
Oh, actually we thought about that. Supermodular games. So one can actually think about projections on the supermodular games as well. The supermodular game characterization is in terms of these cross partials, right? So that's also a linear condition. That's also a subspace. We can think about projection onto those as well, but we haven't done that yet. Yeah. Yes, George.
I'm a bit concerned about the use of the word approximation and also using epsilon. My concern is that it gives the notion that you're getting good approximation. But then if I understand what you say correctly, your error can be fairly large.
Yes, definitely.
And so I'm actually a little bit concerned about that, because and then if you take this the last problem, basically your objective is, I think, is log minus log. You basically take away a second term. I mean, you drop something, and therefore you get this potential gain that you sort of became the first part. If I understand that correctly,
So there's the price part, but let's forget about that.
Yeah, let's drop the price part. So just take your utility. So your signal to noise rate. Then when you drop the one, and you sort of the original function is not a utility function, so to speak, and you make it dropping some term, and now you convert it to a potential function. And the term that you drop could be pretty big.
In the lowest INR case, this approximation is awful. I mean, the error bound actually blows up. But there are very nice tricks, actually. One can think about other potential functions. Yeah, you can do better. And actually, the best is, of course, to consider the closest potential. But this one, I think we just picked because it has this separable structure in the powers, which allowed us also a simple pricing scheme and, had additional benefits.
The other question is, why can this, your last example, not applicable to multi-channel?
Because actually it is now. It wasn't before. Now we have actually cracked that problem also. But here, if you remember, I put a lower bound on the powers that need to be used, which is strictly positive, and that caused the problem with multiple channels. Now what we're doing is we use another potential function. First we remove the non-strategic component, and then we have this nice potential function which doesn't need that assumption, so it's applicable to multiple channels. Yes. Only professors, no students.
Well out of time.
Yeah, just 1 minute. Actually, like for the best response dynamics, you go from from finite game, you go from the stochastic version to mean dynamics, and then from mean dynamics to continuous time. And first, in general, how do you go from the stochastic discrete time to the mean discrete time? And then if you have the continuous time version converges to something, then what does it say about the
discrete time? So there are some results which say, which study the relation between the two. So, and that's the Shama paper that I put as a reference. There are results which say that if the continuous time version converges, that also says something about the discrete time. I'm not sure exactly about the results.
Doesn't guarantee the almost shown versions of the discrete time.
We have to look at it. There are some results. I don't remember the exact statements. But here we're thinking about only the continuous time version. I'm not saying anything about the discrete time.
Okay, thank you very much.
Sure.